o'clock. If you are taking the colloquium for credit, I am the official instructor for the credit portion of this. If you don't know what I'm talking about, don't worry about it. You won't get tested on anything that you hear today. But if you are signed up for Math 175 or Math 375, I have a syllabus. If anybody needs a syllabus, I can hand that out to you. And for anybody who is here, now if anybody is interested in taking the colloquium for credit and didn't even know it was possible, talk to me after Dr. Luttmann's talk, and you can actually earn 1 unit of lower division credit or 1 unit of upper division math credit by coming to the colloquium every week and writing up a reflection paper and maybe doing some other things depending if it's lower division or upper division. So if anybody is interested in that and would like to learn more about it, my name is Brigitte Lama, I'm the chair of the math department. Come talk to me after the colloquium. All right. My second announcement, this is only the first of 12 talks, I think, this semester. So we have the program right here. If anybody would like a copy of the poster, either the small version or the large version, pick one up after the talk. Also, the poster is posted on the math department website, so you can also always check there or download it from our website. Are there any questions about the logistics or anything? All right. Then, before I introduce today's speaker, please come back next week. Next week, our speaker will be Marielle Vasquez from the University of California in Davis, and she will be talking about modeling DNA unlinking. So that will be taking place next week, same time, same place. But today, I'm delighted to introduce our speaker, who is Dr. Rick Luttmann. Rick Luttmann crisscrossed the country from Amherst to Stanford to the University of Arizona, getting his successive degrees, and then in mathematics from a bachelor to a master's to a PhD, and then taught for 3 years in Alaska at Alaska Methodist University before arriving at Sonoma State in 1970, where he stayed until just a year ago, 2014. While he was at Sonoma State, he was very influential in the math department, coaching the Putnam competition, hosting this colloquium for many years, hosting the War and Peace lecture series, being faculty chair, serving on other positions in faculty governance, and creating some of our most sought after GE courses like ethnomathematics, math and politics, and symmetry in arts and sciences. He's probably the most interesting person who ever worked in the math department, having worked as a certified financial planner, creating financial planning software, being associate editor of the American Mathematical Monthly Problem section, authoring 2 books on symmetry, authoring 2 books on raising domestic fowl, authoring several units for the undergraduate mathematics application project, doing field research in Eskimo dancing, tutoring at Roseland University Prep, I think that's current. Is that right? And also tutoring for 10 years at San Quentin. So today he will be talking to us about the apotheosis of Trig, measuring to the stars. So please help me welcome Richard.
Every year my bio gets longer. Pretty soon I won't have enough time to do a presentation. Yeah. Well, you're lucky you came today, because this is going to be the easiest talk of the semester. If you know the Pythagorean theorem and a few trig functions, you'll be in good shape. By now you've probably noticed that we have 2 eyes, and that's not just so we have a spare in case one goes out. The fact is, if we look at the world with 1 eye, it looks all flat. All we can see is line of sight. We know where things are, what direction things are, but not how far away they are. 2 eyes gives us 2 different perspectives. The information we need mathematically to create depth is there. Fortunately, we don't have to think about it. We're wired to process that information into depth. But here's the big problem. Our eyes are only 3 inches apart, So that means if you get out to 100 feet or more, that's not enough of a difference to tell depth. But we look at the sky and we see all sorts of interesting things happening. We have no idea from our visual perception how far away they are. Here's a cloud, here's the moon, here's a star. When the cloud encounters the moon, the cloud comes in front. When the moon encounters a star, the moon comes in front. So we know sort of the order in which these occur. The cloud's closer than the moon, which is closer than the star. But we have no idea that the cloud might be a couple of miles away, the moon is 250,000 miles away, and the star might be uncountable tens or hundreds of trillions of miles away, so far that the concept of a mile becomes almost meaningless as a unit of measurement. Nonetheless, we hear all the time about distances in the universe. And it's my purpose today to talk about how we know how far away things are up in the sky. It's a fairly simple story, except for the fact that we need different techniques as we work further and further away. So there's kind of a ladder here, and we'll work our way up using different techniques as we go. The first thing we need to talk about is the Earth. How big is the Earth? Now, this just in, the Earth is round. Yes, yes, I know. It's a surprise, it doesn't look round, it looks flat, but that's just because it's big compared to us. When you get very close to a curved surface, it looks flat. But it's easy to tell that the Earth is curved. Go down to the Marin Headlands and watch traffic go in and out of the Golden Gate. You see a freighter, say, that's going off to Tokyo. At first, no problem, it's sitting there on the ocean, there's water all around it. But after it gets out a ways, you'll suddenly see it's run out of water. There's nothing behind it. And after that, it starts going down behind the water. Now, see, if the Earth were flat, you could see the ship go all the way to Tokyo. Now, of course, it gets smaller and smaller as it goes, and you'll need a higher and higher power magnification. But you could see it, no matter how far away it is, if the Earth were flat. So I'm going to use that idea to determine the size of the Earth. We can do it by comparing our height above the sea level to how far it is to the horizon. The only problem is it might be something on the order of 30 miles to the horizon. How are we going to tell that exactly? So I wanted to show you first a technique for figuring out how far away a ship is. So you'll need some equipment. One Golden Gate bridge with 2 towers, an assistant, a long tape measure, a mile long will do, 2 sextants, those are devices for measuring the angles between 2 lines of sight, and you need a signaling device of some sort. It could be a semaphore, cell phones, high or low tech, it doesn't matter. You have to be able to communicate with your assistant, because what's going to happen is you're going to climb the south tower of the bridge and your assistant's going to climb the north tower. Now, by the way, if you actually do this, don't mention my name because I'm going to deny everything. So you get up there, and by the way, while you're up there, I hope you brought the tape measure because we'll need this for later. Drop the tape measures and down to the water and see how high you are. We'll need that in a minute. But what you're going to do is wait until you see a ship that's exactly on the horizon. Now, admittedly, there's a little bit of fuzziness about when that happens. That's why you have the signaling device. It's important that you and your assistant make your measurements at the same time. So when you're ready, when you think it's right on the horizon, you signal your assistant, and then you each measure the angle between the other tower and the ship. So the picture looks something like this. This down here is the Golden Gate Bridge. You see, it's golden, right? And so here's you on the south tower. Here's your assistant. You're going to measure these angles, S and N. The angles of the triangle add up to 180 degrees, so you just add those 2 numbers together and subtract from 180, and you'll be able to tell what the angle is up here at the ship. Now you know the shape of the triangle. So all you need to do is figure out how far it is across the bridge. That's what this long tape measure is for. We need the length of the main span between the two towers. And then that nails down the triangle exactly. Everything else we want to know about the triangle we can now find out. The law of sines would be helpful here. The law of sines would say that the length of this side here, from U to the horizon, divided by the sine of this angle across from it, is equal to the length of the bridge divided by the sine of this angle. You have to make sure you're working in the right units. So probably you would measure the length of the bridge in feet, but you'll have to convert that to miles. So I made up some reasonably appropriate numbers here. Let's see. So I tried focusing it. I think it's too dusty. Is that better? Okay. Yeah, this lens is very dusty. I don't think that they've been dusting it recently. So suppose that the south tower, the angle is 71 or so degrees, and the north tower is 107, and the bridge is, did I put that here somewhere?
At your procedure, 4,200 feet.
Yes, 4,200 feet. It's about 0.78 or so of a mile. So you do the arithmetic and you find out that the ship is 33 and a bit miles away at the horizon. All right, now with that information, you can measure the Earth. We're going to look at the same situation, but from a different perspective. What I've done here is I've sliced through the Earth with a plane. The plane contains the center of the Earth, it contains the ship, and it contains you up there on the top of the north tower, south tower. We are at least temporarily assuming the Earth is actually a sphere. It is not quite, but close enough for our purposes right now. Now, when the ship is on the horizon, that means your line of sight is just grazing across the Earth, and so it's a tangent. And the tangent is perpendicular to the radius. So we've got a right triangle here, and the Pythagorean theorem will be useful to us. This side here is, we'll call it r, the radius of the Earth, which is what we want. This distance here is, I'll call it s. We just measured that, the distance to the ship. And the hypotenuse is in two pieces here. It consists of the radius plus the height of the bridge. So I hope you remember to measure it. It's about 746 feet. Again, you have to convert that to miles. So the Pythagorean theorem says r squared plus s squared equals r plus h squared. We have three letters here, r, s, and h. R is what we want to find. S and h we know. We just have to solve for r. At first blush, it looks like it's a quadratic equation. But as soon as you expand out the right-hand side, r plus h squared, that's right here, you get an r squared, which is going to cancel the one on the other side. So it really becomes a linear equation. It's easy to solve. And you find that r is equal to s squared minus h squared over 2h. Just plug in the s and h, and you can find the radius of the Earth, 3,969 miles. Now, I mentioned over here that the Earth is actually not quite a sphere. For one thing, it's spinning and it's kind of plastic, so it bulges at the equator. It's actually about 13 miles thicker from across the equator than it is from pole to pole. In addition, most of the land mass of the Earth is in the northern hemisphere. Try taking a look at a globe upside down. You'll mostly see water. So it's not quite a sphere, but it's certainly very close, and close enough for our purposes here.
So with your radius then that you calculated, how
Oh, I made up the number so early. I worked backwards. Now, just as an aside, this equation relating R, S, and H, we use it with an S and an H to find R. R is not going to change, but S and H can from time to time. It can be different heights above the sea, and there's different distances to the horizon. This formula allows you to solve for S, the distance to the horizon, when you know H, your distance above the water. And it works out very nicely. Here's this formula here. D, I'm calling it now, the distance to the horizon, is the square root of 3h over 2, 3/2 h, where h is in feet, but the distance you get is in miles. It's a very convenient rule. It's found from this equation by solving for S, using what we know about R, and making, well, let's say there's two little footnotes. One is, it says S squared minus h squared, but S is a lot bigger than h. And S squared is really a lot bigger than h squared. So drop the h squared, it's not going to make much difference. And it makes it easier to solve the equation. Also, we want to go from height in feet to distance in miles. One of the reasons this formula works out so simply is that by the sheerest good luck, the radius of the Earth in miles is almost exactly 3/4 of the number of feet in a mile. That's why this simplifies this way. So let's see how we use this. Suppose you're standing at the edge of the sea and your eye is 6 feet above the surface of the water. Take 6, increase it by half to 9, take the square root, it's 3. It's 3 miles to the horizon in that case. On the other hand, let's suppose you go up to the top of Mount Tamalpais and you're 2,400 feet above the sea. Increase that by half, you get 3,600. The square root is 60. You can actually see the horizon 60 miles out. This rule was actually very useful to mariners of old. 19th century, for instance, there was a lot of whaling activity. These ships would have a crow's nest way at the top of the highest mast, because from up there you have the biggest view. And this little rule of thumb would allow sea captains to know, on the basis of how high their crow's nest was, how far they were able to see. All right, so we know now how big the Earth is. But this is not the only way to do it. And I wanted to tell you about another way, which goes back a very long way to ancient Greece. You know, when I was in grade school, we were taught that Columbus was the first person to think that the Earth was round. Well, he might have been the first European of the 15th century to think that. Remember, in 15th century Europe, the intellectuals were still counting angels dancing on the point of a needle. But way back in the Greek era, Eratosthenes measured the Earth. This was in the 3rd century BCE. And this is how it went. There was a city called Syene, which is near present-day Aswan in Egypt. It happens to be on the Tropic of Cancer. At noon on Midsummer Day, the sun is directly overhead in Syene. And you can tell that, they could tell that, actually, because there was a deep well, and at that time, on that day, they could see the sun reflected in the water deep in the well. At the same time, a vertical post in Alexandria cast a small shadow. So Eratosthenes pictured it like this. Now, he did not prove that the Earth was round. He assumed it. And he also assumed the sun was so far away that for all practical purposes, its rays were coming in parallel. So he measured this angle here between the post and the sunbeam. It was 7.5 degrees, which happens to be 1/48th of a full circle. This angle down here is the same by alternating interior angles. So this angle is 1/48th of a full circle, and this little piece of the arc up here then is 1/48th of the full circumference of the circle. So all you have to do is multiply this distance by 48, and you'll have a good estimate of the circumference of the Earth. From Syene to Alexandria is what the Greeks called 5,200 stadia. We assume that by a stadium they meant the one in Olympia, where the Olympic Games of old were held, and it's about 500 feet long, a tenth of a mile. So with that in mind, we come up with this figure that's very, very close to what we accept today as the circumference of the Earth, about 25,000 miles. I put down here this devil's advocate scenario. As I say, he didn't prove the Earth was round, he assumed it. If the devil's advocate comes along and says, no, I believe the Earth is flat, and the sun is up here like a street light, and you know, when you walk underneath a street light, your shadow is 0, and if you walk away a little bit, it gets longer and longer. So with that scenario, you convert this 7.5 degree angle here into this one up here, and what you need is the cotangent of 7.5 degrees. That would be the ratio of the height of the sun to this distance here. And when you go through the arithmetic, you find out that the sun would be 4,000 miles high. But we don't believe that. All right. Enough about the Earth. Let's talk about the sun and the moon. It's a remarkable coincidence that the apparent size of the sun and the moon in the sky are almost the same, about half a degree in diameter. There are actually slight variations in their size because there's slight variations in their distances from us. So close together are they to being the same size that sometimes one is a little bigger and sometimes the other. Now the reason for this change is that the moon is not moving around the Earth in a perfect circle. It's actually an ellipse with the Earth at one focus, and so the distance varies a little bit. And when it's closer, it appears bigger, and it's farther away, it's a little smaller. Similarly, the Earth is going around the sun in an orbit that's actually elliptical, again with the sun at one focus, so the distance varies and the size of the sun varies. In both cases, the orbits are almost circular, but there is a slight difference in the course of the orbit. So you can see this, see how close the moon and the sun are being the same size at the time of an eclipse of the sun, when the moon moves across the face of the sun. If that happens at a time when the moon is relatively farther away and hence smaller, and the sun is relatively closer and bigger, the moon's disk isn't big enough to cover the whole sun. And what you'll see is a great big black circle with a flaming border around the edge, a ring of fire. That's called an annular eclipse, from the Latin word for ring. At the opposite extreme, the moon will cover the sun's disk, and it'll stay covered for a little bit, not very long, maybe I think the maximum is about 9 minutes. From the time that the moon's disk, the leading edge, finally covers the whole disk of the sun, and it gradually moves by, and 9 minutes later it starts to reveal the sun's disk again at the trailing edge. So what this means is that the sun and the distances to sun and moon and the sizes of the sun and moon are essentially in the same proportion. If, as sort of suggested by my sketch here, the sun is 5 times as far away as the moon, then it would be 5 times bigger. It's actually a lot farther than that, but the point is we know that we know that much at this point. Eventually I'd like to know how big is the moon, how big is the sun, how far away is the moon, how far away is the sun. At least we know this much for now. Well, I want to go back to another very smart ancient Greek, Aristarchus, because he thought of an interesting way to figure out what that ratio of the sun's distance to the moon's distance is. The moon, of course, moves relative to the sun. New moon, they're pretty much lined up, and then we see a little crescent moon, and it gets bigger and bigger, and then it's half full, and then it goes into the gibbous phase, where it's more than half, and eventually it's full. So Aristarchus proposed looking at the moon at exactly that moment when it's half full. The boundary between light and dark would be a straight line. It's an arc of an ellipse. But when that happens, it must be, here's the sun, here's the moon. We're seeing the moon from directly to the side of the light coming from the sun. So this up here would be a right angle. And that means, once again, we have a right triangle here. So Aristarchus' idea was to measure this angle, and then the secant of this angle would be the ratio of this side, which is the distance to the sun, to this side, which is the distance to the moon. So that's what he did. And he got 87 degrees, which leaves only 3 degrees over here. And the secant of 87 degrees is about 20. So he inferred that the sun is about 20 times as far away as the moon, and therefore about 20 times as large. Now, it turns out his theory was impeccable, but he was using relatively crude measuring devices that were available then. And it turns out that this angle down here is much closer to 90 degrees than he thought. And there's much less left over for down here. This angle is 89 degrees, 51 minutes. So this is only 9 minutes of arc, instead of what Aristarchus thought, which 3 degrees was 180 minutes. So it's only a 20th as big. And due to the fact that the cosine's derivative, where it crosses the axis, is -1, it turns out that the ratio is actually 20 times as big. So using modern measurements, we infer that the sun is 400 times farther away than the moon, and accordingly 400 times as large. Well, that's also interesting to know.
For large means radius the same?
Good question, but yes, I'm talking about linear distances at this point. Whether you measure the radius, the diameter, or the circumference, are linear distances, and that's the ratio we're talking about. I'll come back to that point in a minute. Now I might as well tell you now, since you brought it up. When I was a boy, I was fascinated with astronomy. I read every book I could get my hands on, and I memorized all these facts about planets, their sizes and orbits and stuff like that. But there was one thing that puzzled me. Some books said the sun was 100 times as big as the Earth. And others said it was 1,000,000 times bigger. Now, if one of them had said 107 and the other said 100, I'd say, okay, close enough. One of them's rounded off. The other was being more accurate. But 1,000,000 versus 100, ooh. I suppose I should have been able to figure that out. I didn't. But in retrospect, it's clear what's going on. One book is talking about the ratio of linear distances. The diameter of the sun is about 100 times the diameter of the Earth. But the volume ratio would be the cube of that. And that is about 100. We'll get more accurate measurements of those numbers in a few minutes. But first, let's talk about how we can nail down just how big and how far away the moon is. We can do that by observing carefully a lunar eclipse. This is when the moon passes through the Earth's shadow. Now, over here's the Earth, and this big black wedge is its total shadow. When you're inside that wedge, you can't see the sun at all. No part of it. Astronomers call that the umbra, from the Latin word for shadow. If you go just a little outside of this black line, you can start to see parts of the sun. And so you're in a partial shadow, which the astronomers call the penumbra, from the Latin word pen, meaning almost. As in peninsula is almost an island, penultimate is almost the last, and so on. we can actually find out where this point is out here at the end of the shadow. Because we know this angle here, that's that half a degree that I mentioned before. Sure, technically it's a little smaller because we're a little further, but the difference is negligible when you're talking about a half a degree. If you express this angle in radians, that's equal to this arc length divided by this distance here. And for such a small angle, there's really a negligible difference between the arc length and just the diameter of the Earth. And we know the diameter of the Earth, we know the angle. We do the arithmetic and find out where this point is. It's almost 900,000 miles out into space. Now, on this diagram, you see another wedge going the other direction. It's the dashed blue line. The moon fits in there because, remember, it's half a degree also. So if it's relatively close to the Earth, it's going to have to be pretty small to fit in that wedge. And if it's farther, then it's larger. So think about what happens during an eclipse when the moon passes through the shadow. If it were close, and therefore very small, it would take a relatively short time to fully enter the shadow. That is, from the time it starts to enter until it's fully in, compared to how long it stays in the shadow. Got a long way, much longer way to go than its own diameter. On the other hand, if it was way out here, the leading edge of the moon is going to enter the shadow and then exit the shadow before the trailing edge has even entered. So, what we need to do is figure out how long does the moon stay in full eclipse. And it turns out it's 1.734 times as long as it takes to get into the shadow. From that information, I'll let you do the algebra, we can infer that the moon is 0.2678 of the way from the Earth to this point out here. And that it's also 0.2678, a little bit over a quarter, as large as it would be out here, which is the size of the Earth. So, the moon, in diameter, is a quarter as big as the Earth, a little bit more. I got the exact measurement by modern standards, a little over 1,000 miles in radius. And its distance then would be about 240,000 miles. Now remember, it does vary. So you have to take this calculation with a bit of grain of salt. It actually varies between about a little over 225,000 to a little over 250,000. But clearly, 240,000 is a good estimate. Notice that if you're interested in real estate, there's a lot more real estate on the Earth than there is on the moon. The inverse of this number here is the 3.734. In other words, the Earth, put it the other way around, is about 3.7, and 3.7 is a little bit more times as big as the moon. Square that, and you get the ratio of the surface areas. Cube it, and you get the ratio of their volumes. And those numbers are here for you. We might be tempted to infer that therefore their masses are in the same ratio, but that requires another major assumption, which is that they have the same average density. We have no mathematical way of dealing with that question. In fact, the Earth is probably more dense than the moon. Now remember, once we know how far away the moon is and how big, then we can transfer that information to the sun. And we find out that the sun is a little under 93 million miles away, and that its diameter, its diameter is about 866,000 miles, over 100 times the diameter of the Earth. And again, if you square that ratio, you'll get the amount of surface area that the sun has relative to the Earth, and if you cube it, you get the ratio of volumes. And it's sobering to realize that the sun could be filled up with 1.3 million Earths. Because you have to bash them up in little pieces. The spheres don't fit together. But the sun has as much volume as 1.3 million Earths. Okay, well, we made a lot of progress. Let's next turn our attention to the planets. There are 5 planets visible to the unaided eye. And they move in the sky relative to the background of stars. Of course, everything rises and sets with the rotation of the Earth. But the stars all stay fixed relative to each other, except for these 5 wanderers. The word planet comes from the Greek word for wanderer. Now, our intellectual forebears did not understand what was going on in the heavens at all, and so they attributed divine powers to these planets, and that's why they are named with names of the gods. Mercury, which is the swiftest planet and moves faster than the others, is named for the winged helmet god of the messenger. In older times, dimes had a picture of the head of Mercury. Now it's Franklin Roosevelt. Venus is the morning and the evening star. It's very beautiful in the dawn and in dusk sky, so it's named for the goddess of beauty. Mars is red. That's the color of blood and fire, so it's named for the god of war. Jupiter is the largest planet, so it's named for the king of the gods. And Saturn is the slowest planet and also very dim, so it's named for the god of old age. Throw in the sun and the moon, and you've got 7 objects up here in the sky that move around. And as you may have noticed, we also have 7 days in a week. Coincidence? I think not. We have a Saturn's day, we have a sun's day, we have a moon's day. To understand the rest, you have to go through Norse mythology. There's Woden's day, which is named for Woden or Wotan, who is the king of the gods in Norse mythology, and it's the equivalent of Jupiter. Thor's day, Thor is the god of thunder, and it's war, the equivalent of Mars. And Frida's day is named after Frida, the goddess of beauty. Notice I skipped over Tuesday, because I don't remember the name of the Norse equivalent of Mercury. But that's where they come from. Now, the 5 planets we can see with the unaided eye fall into 2 classes. Venus and Mercury never move very far from the sun. They move back and forth around. Mars, Jupiter, and Saturn move all the way around. So we infer that the latter group, their orbits are bigger than ours, and that's why they go all the way around, whereas our orbit is bigger than Mercury and Venus, and that's why they don't go very far from the sun. So it looks sort of like this. Here's the sun, here's the Earth, this is the orbit of Venus. Now, of course, both the Earth and Venus are moving, but Venus is moving faster. You know, relative to the Earth, Venus is moving around like this. And if you think of the line of sight from Earth to Venus, relative to the line to the sun, as it moves over here, it's moving farther, the angle that is widening, until it gets there, and then it starts to decline again. Well, standing here on Earth, we can figure out what that maximum angle is. And when that maximum angle occurs, our line of sight is just grazing across the edge of Venus's orbit, so it must be tangent to it. And that means it's perpendicular because there's a radius here. And so once again, we have a right triangle with the right angle in Venus. We already know this distance here. We just figured out a few minutes ago. It's almost 93 million miles. And we can measure this angle, and what's it turned out to be? It's here somewhere 46 and something degrees. The sine of that angle is this side divided by this side. That sine is about 0.7. I have trouble seeing this because of the light behind it. Is that it? 0.772, yes. That's the sine, and that's the fraction of Earth's orbital radius that represents Venus's. Now, astronomers call, for convenience, the distance from the Earth to the Sun an astronomical unit. So basically what we're saying is Venus is orbit is 0.2725 astronomical units. But if you want to see it in miles, I've got that there for you as well. And likewise for Mercury. It doesn't move as far from the sun. What is it, 22, 23 degrees, I think. And so the orbit is much tighter. Now, how about their orbital periods, their years? We can't observe that directly because we're moving as they are. What we can see is that Venus goes through a complete cycle from being the morning star to the evening star and back again to the morning star in 584 days. (584, by the way, turns out to be 8 times 73. And 365, which is the length of our year, is 5 times 73. So the ratio of the Venus cycle to our year is 8 to 5. 2 small consecutive Fibonacci numbers. I'll just let you think about that. It's probably meaningless. But the idea is, what we'd like to infer from the Venus cycle, 584 days, how long it actually takes to go around the sun. 584 days is the lap time. You can imagine 2 race cars going around a track. And one's a little faster, and it gradually gets ahead of the other one. And sooner or later, it comes up behind it and catches up. And it has lapped it. It's going one more lap. And that's what's going on with the planets. Venus is faster than we are. And 584 days represents how long it takes to lap us. From going, say, lying straight between us and the sun to a little bit later, it's again back between us and the sun. Well, it's a simple algebraic exercise, which I'll leave to the interested reader to infer from that what its actual year is. And it turns out it's 225 days. And likewise, you can do that with Mercury. It really moves fast. Remember, it's the wing of God, the messenger of God. It's 88 days. How about the other planets? Well, we can't use the same trick with these other planets. But what we can do is rely on a very smart dude named Kepler, who has provided us with several important laws. They're not laws in the usual human sense. They're patterns, basically, that nature seems to obey. He came up with 3 laws of planetary motion. He was working with some very, very precise and complete records that a Danish astronomer named Trig had provided in a generation before. He came up with 3 rules of planetary motion. One of them we've alluded to already, and that is the planets go around the sun in elliptical orbits with the sun at one focus. The second law, we don't need to dwell on it here, it has to do with how the speed of the planet in its orbit varies as it goes around and is ultimately farther and closer. But the third law I want to talk about, because it talks about the relationship between the planet's orbital periods and the orbital radii. It took him a while to figure this out, I presume, but it turns out if you square the orbital period expressed in Earth years, and you cube the orbital radius expressed in Earth radii, you get the same number. So if you try that with the Earth, well, our year is 1, and our orbital radius is 1, and 1 squared over 1 cubed is 1. And it will always turn out to be the same number. So it just turns out that happens to be the case with Mercury and Venus. So this becomes his third law. And now we take a chance that if this law applies to the first 3 planets, it probably applies to the next 3. I mean, yeah, intellectually it's a leap, but we seem to live in a pretty orderly universe. I mean, what did we do to deserve it? I don't know. But things seem to follow patterns. So on the basis of that, we can say, well, look, we can observe the lap times. In this case, Earth is lapping them. We can infer from that their orbital periods. And then we can use Kepler's third law to figure out their orbital radii. And it turns out that Mars is about twice as far as we are. 4 times away is the asteroid belt, which possibly once the planet is broke up. Let's say Krypton. And 8 times as far away is Jupiter, and 16 times is Saturn. Nice little pattern there. That's known as Bode's law. That the distances seem to double as we go out. Now, I wanted to just talk about kind of an aside here, but it's something we're going to need to worry about here in a minute anyway, and that's the speed of light. By human standards, light seems to be virtually instantaneous. Some of you are back at the back of the room, or maybe 20 or 30 feet from the screen. There's actually a bit of a lag time between when the light leaves the screen and when it gets to you, but it's so small you wouldn't notice. It's 20 or 30 nanoseconds, billionth of a second, because light moves about 1 foot in 1 billionth of a second. But on the scale of the universe, the finiteness of the speed of light becomes very important. So how do we know how fast light is moving? Well, here's one way to tell. Galileo was the first person who actually seriously used the telescope. It had been invented by somebody else not long before he lived, but he really used it for scientific exploration. And one of the things he discovered was that Jupiter has moons. Now, it actually has quite a few of them, I think a couple of dozen even, but there's 4 of them that are big enough to see with the size telescope that we have. Io, Callista, Europa, and Ganymede. Isn't this amazing? 8 times as far away as the sun, yet we still figured out their names. Now, these moons were clearly moving around Jupiter. And it was the first time in human intellectual history that people had seen something in the sky moving around something other than the Earth. The cosmology of the time said the Earth's the center of everything. Everything moves around the Earth. The Catholic Church in particular, now their field is supposed to be theology. But they were sliding over into cosmology as well. And they did not like to hear about what Galileo had discovered. Many of them refused to look in the telescope because they said, so he said, look, just take a look. No, it couldn't be. Well, you probably know the story of how the church reacted to Galileo. He was no problem. But here's what I wanted to talk about. Let's suppose that we catch things when Earth is in line with the Sun and Jupiter. Earth is between the Sun and Jupiter. And let's suppose that's when we make a schedule for these moons. I mean, after all, you can tell each one, and over here on the left side, and it crosses in front of Jupiter, and then it's over on the right side, and it goes behind Jupiter. So we can come up with a schedule for each of these moons. And then as time passes, and the Earth moves this way, and Jupiter moves this way, pretty soon, because the Earth's moving faster, at least in angular measure, Earth's is over here, and Jupiter's here. This is the second position. Now Earth is opposite the Sun and Jupiter. Well, it turns out while that's happening, the moons are falling behind schedule. In fact, at this point, they're about 17 minutes behind schedule. 998 seconds. And then as time continues to pass, and the Earth continues to move this way, and Jupiter this way, pretty soon the Earth is between Jupiter and the Sun again. And while that's happening, the satellites of Jupiter are catching up. And they're back to where they originally, back to their original schedules when they get here. Well, clearly, the moons of Jupiter have no obligation to the Earth. There's no way that the fact that we are observing them at certain times is going to have any effect on what they're actually doing. This delay then must have something to do with the signal that's bringing information to us about these moons. When Earth and Jupiter are in positions 1 and 3, the light has to move only this far. But in the second position, it has to move this far, and then all the way across the Earth's orbit. And the diameter of the Earth's orbit is 186 million miles. Remember we figured out a few minutes ago, the radius is 93 million, double that. So if you divide that by the 1,000 seconds almost, that it takes light to move that, you get 186,000 miles per second. That's how we could infer the speed of light. Now, Galileo probably could have done that, but he didn't. He died in 1642. But just over 3 decades later, a German physicist named Römer did this calculation. It was in 1675. So since then, we have known about this extraordinarily large speed of light. It's so fast, as I say, in a nanosecond, it goes a foot. It could go the equivalent of 7 times around the Earth in a second. The moon's 250,000 miles away. It could get there and back in less than 3 seconds. Almost 100 million miles from the sun, we get the light from there in 8 minutes. Within the last month or two, there's been some news about some photographs that were taken recently by NASA of Pluto. Have you seen that in the paper or on the television? One of our satellites flew by Pluto and took a lot of pictures. It took 4.5 hours to transmit those images from Pluto back to us because it's something like 2 billion miles away. So now we can use a new standard of distance. The sun is 8 light minutes from us. Pluto is 4.5 light hours from us. And we're going to find that when we start talking about the stars, and I did promise in the title of my talk to talk about the stars, so we'll get to that. Oh my, maybe we won't. We're going to need light years. Yeah. I think in light of the fact that time is slipping away here, I will summarize a little bit. Maybe I have a moment to talk about parallax, which is really how we start finding distances. You know, if you walk up and down, say in front of a forest, the trees that are close to you will move through a wide angle, and those that are further away will a lesser angle. That's called parallax. And as the Earth goes around its orbit, we see this parallax phenomenon with respect to stars that are relatively close to us. And knowing that angle, the parallax, and the diameter of the Earth's orbit, we can figure out how far away these stars are. Now, the parallaxes are very, very tiny, but astronomers are very, very careful and precise people. It turns out with our best telescopes, we can measure parallax as small as 1/2000th of a second of arc. That's a small enough angle that you could see a CD on the moon. We find out that the nearest star to the Earth, which is called Alpha Centauri, it's the brightest star, the Alpha star, in the constellation of Centaur. We can't see that from here, it's in the southern hemisphere. That's 4.5, almost 4 light years away. And then there are other stars we can measure. We can measure actually out to over 12,000 light years, and there are literally hundreds of thousands of stars in that range. But there's a lot more stars than that. So let me just summarize what we have found. The rest of the story involves things like Cepheid variables and Doppler shift and the red shift in particular. But let me just paint a picture for you of what we now know about the structure of the universe. When you go out at night and look at the sky, just about everything you see is in a large conglomeration of stars known as the Milky Way galaxy, which is shaped something like a puffy pancake. It's 10,000 light years thick and 100,000 light years across. Now, our human forebears left Africa about 90,000 years ago. If a light ray had started at one edge of the Milky Way, when our ancestors crossed out of Africa, it would still be moving across the galaxy, and it would only be 90% of the way through. It would still have another 10,000 years to go. I mean, this is how vast we're talking about. Now, when you look at this at the night sky, well, see, we're not at the center of this disk. We're out a ways, about 60% of the way out. So from our vantage point, yeah, you can see stars in every direction, but bulk of them are in one direction. And that's why in the summer sky, you can see this swath across the sky that looks like spilled milk. It's stars, but they're so thick that they almost look continuous. And that's where the name Milky Way comes from. And the Milky Way galaxy, by the way, is a bilingual redundancy because the word galaxy comes from the Greek word galactos, meaning milk. Now, there's one thing you can see in the sky, if you're lucky, if it's clear and dark and you're standing on a mountain in Utah. One thing that's not in the Milky Way, and that's the Andromeda galaxy. It's another galaxy very similar to ours, a little bigger. It is 2 million light years away. Now, bear in mind, that means not only a big distance, but when you look at it, you're seeing light that started there 2 million years ago. Hey, for all we know, Andromeda blew up 1 million years ago. And the information to that effect is being carried on light signals that are only halfway here. And it'll be another 1 million years till we find out. And that's just the beginning, because with our best telescopes, we can see things that are almost 4 orders of magnitude farther away. The farthest things we see are 10, 12, 14 billion light years away. One final comment I wanted to make is just about everybody's favorite subject, space travel. There's a lot of problems with space travel. Propulsion, running into things, supporting human beings in space where there's nothing that we have evolved to need. But we can probably overcome some of those things. We already have been to the moon, and there's talk about going to Mars. I would say maybe before we destroy ourselves, we might be traveling around the solar system. I will go out on a limb and venture to say human beings will never leave the solar system. Even if you were moving at the speed the Earth is going in its orbit around the sun, which is 18.6 miles per second, fast enough to get from here to the Golden Gate Bridge and back in less than 5 seconds, fast enough to get around the whole Earth in 20 minutes, that's still only 1/10,000th the speed of light. So you set off for Alpha Centauri, and it'll be 80,000 years before you get back. Remember, 90,000 years ago, our human ancestry left Africa. So we're not going to go there. And if there are other intelligent civilizations in the galaxy, and that's a big if, because I don't think there are any, they can't get here either. So forget about flying saucers. There may be unidentified flying objects, yes, literally. Flying objects, I don't know what it is. But flying saucers, it's not going to happen. Barring, of course, the discovery of some new principle of physics, but we don't know that we haven't discovered yet, but we don't know there even is. Well.